So we click on the Take Up tab. Once again, we have an auto and a user button at the top. When in auto, the program will select a tension and a weight for you based off of 6 different values, basically calculating out what's the minimum take-up tension required to prevent sag during running, during acceleration, during drift, and then also looks at slip for running, acceleration, and drift, and then it finds the largest number there and adds 10% to it. So acceleration slip is the largest of those 6 values and adds 10%, and it pops in 3,618 pounds of tension required to prevent that. If I flip this over to user, it allows me to edit those values, and let's say we actually have a nice round value of 4,000 pounds of tension on this conveyor. I can lock it in. Now the program will when I'm in user, it locks it in, and now the program won't change this based off of if I want to test anything else, what happens to this conveyor if insert anything there, and you can see if your take-up is still valid for that. So we have our take-up set up. Let's make sure our pulleys are set up. I'm going to click on pulleys, and I'm only going to do the basic version here, and basically when I click on basic, it removes any calculations for shafts, deflection, bearings, those sorts of things, and just prints out a T1 and a T2 tension for each pulley based off of the wrap you have there. I'm going to expand the folder and look and see that we only have these 3 pulleys as we expected, because there's only 3 pulleys in the flights tab as well. And it'll say at flight 5, flight 6, and flight 11 we have pulleys, and their T1 and T2 tensions are printed out for you. This would be something to give to a pulley manufacturer who's making the pulleys for your conveyor, or maybe looking to replace pulleys on your conveyor. You can give them these, and they can design the pulleys around it when you're in basic mode. If you're off of basic mode, it allows you to do the calculations yourself, and even further, if you're in advanced mode, advanced design mode, it allows you to do even more detail around specific hubs, specific bearings, and shaft sizes as well. So I clicked it in basic mode because we're only going to do the basic calculations for this quick example, and we're set there. So I'm going to contract this folder, hide what I don't need to see, and say that our pulleys are set up as well as we want to right now. Later on we can set them up in more detail than we currently have. So pulleys are set. Let's click on vertical curves. Clicking on vertical curves, we see that once again we have an auto and a user radio button. Basically auto looks at before I get in, let me expand this folder so we can see all of it. Auto basically looks at all the values to prevent excessive liftoff if it's a concave curve, and high or low edge radius tensions or edge tensions and center tensions in the belt. Per SEMA, it makes those calculations, then looks at the largest number throughout all of these, and then sets the radius of the curve to fit that. In this case, this first curve at point number 2 in our flights is a concave curve, and during acceleration, the liftoff or the radius required to prevent any liftoff during acceleration is 771. So it puts that right there. And this is the carry side part of the curve. You'll notice that matched up for the return side at flight 10, which is the return side version, also number 2. It basically looks at it does all the calculations as well, and then if that's larger than the carry side version, 771, it'll put it in there. In this case, these 500 numbers are not larger than 771, so it keeps that 771 value for what we have. And this happens because we have automatic return segments that the carry concave curve and the return concave curve are matched up. Because you know that they are the same curve. If you are in user return mode, where the carry side of the belt does not necessarily match the return side of the belt, these would all be separate numbers, and they would do the calculations as such. For the flight number 4, the convex curve, it basically looks at the edge, the tensions of the belt at the edge and then tensions the belt at the center of the belt and figures out to either overstress or understress them what the radius would need to be, and then picks the value there and prints it out. We also output a load per idler. Any excessive loads due to the curve radius will be calculated out and recommends an idler spacing in order to prevent those excessive loads. So we'll click this into user and use all the recommended values, or actually we are in a existing conveyor. Let's say in this case we have an 800-foot radius for our concave curve and a 75-foot radius for our convex curve, and say that's what we designed for, and they're set there. And any changes we make now to the entire conveyor system, we'll be able to test and see if those curves are okay. They'll turn red or not red depending on if they're okay or not. So I'm going to contract this folder and click on the last tab and just point out here, and so you can see where the material would travel as it leaves the belt, leaves the pulley, and you can design a chute based off of that. So there we are. We have our conveyor fully input. I'd like to mention here that we have not designed this conveyor yet. We have basically just input the components. Once you input the components, the next step is to put it through its phases. Put this conveyor through its tests. Put it through, if it gets cold outside, what happens? If it changes the loading, as you would see, what happens in real life in this conveyor, and go through your steps and see what turns red, what components need to change. You can do your what-if scenarios. If I change different componentry, what happens to the entire system? And the belt analyst will allow you to calculate all those changes, and you can run your tests. So that'll conclude this tutorial, this basic tutorial on how to input a conveyor. Hope you learned something, and we'll see you in the next tutorial.